Highway, Wisconsin Autonomous, and for Innovation One, we attempted to create an advanced filtration and smart intake methods to reduce allergens in the cabin of ride-sharing vehicles. This is a quick overview of the presentation. The contaminant that we chose was allergens. Allergies affect over 1 billion people worldwide and are one of the most predominant chronic diseases. Allergic rhinitis, the scientific name for allergies, can lead to worse and possibly deadly diseases like asthma and can also cause some serious nasal congestions. It also costs the US about tens of millions of dollars per year. Many brands of vehicles use systems that are effective in filtering harmful pollutants to some extent. However, most of the harmful pollutants still manage to enter the cabin through air vents or other openings. So vehicles serve as a hotspot for allergens if not cleaned properly. What and who do allergens affect? So allergens can affect people by causing sneezing and coughing that can lead to spread of other diseases. They can also cause vulnerability to other diseases because of a weakened immune system. Allergens can also affect pets by causing respiratory problems in them. It can also react with their skin and lead to some serious skin infections. Allergens also affect the insides of the car by reacting with the seat coverings. When they react with seat coverings, they can discolor them and can also make them smell bad. Allergens can also react and form residues on the glasses of vehicles, which results in fog. This fog in the car might result in some serious visibility at that. So to address this problem, we have a few solutions that are broadly categorized into the hardware and software group. Within the hardware group, we have the Cyclonic Separator, Hepa Filter, and the Enthalpy Wheel, and within the software group, we have Air Quality Monitor and the WM Monitor.
Alright, so now I'm going into our hardware solution. I start with Cyclonic Separation. So a cyclonic separation, an example of the unit can be seen on the right side there. So simply put, it creates a spiral vortex with the intook air. This spiral vortex is moving very quickly, and the large particles in the air have too much inertia to maintain this tight curve. So they hit against the outside of the cylinder, and they fall to the bottom, while the cleaned air goes to the top and goes to wherever you need it. So these are used in a couple different industries. Sawmills use them to remove sawdust from their air. Industrial kitchens use them to remove grease from air. And Dyson vacuums use them to remove the dirt from the air. So our plan is to use this in the HVAC intake system of our vehicle. And we're going to use this as a pre-filter to remove some of the large particles. So a couple advantages of cyclonic separation is that it's cost saving. Using it as a pre-filter will mean we don't have to replace our next filter as often, and it's a very robust system. Once they're installed, they don't need any maintenance. So the next step will be a Hepa filter. Hepa stands for High Efficiency Particulate Air Filter. So the filters used in most cars are carbon filters, and they capture about 98% of particulates 5 microns or greater. A Hepa filter captures 99.97% of particulates 0.3 microns or greater. So as you can see, that's much greater. So the reason most cars don't use Hepa filters is A, because they would have to be replaced more often, and B, since they're so thick, they reduce airflow and increase energy use. So our solutions to that was A, the cyclonic separation pre-filter, and then to address the energy use, we're going to use an enthalpy wheel. So an enthalpy wheel contains a desiccant material that exchanges heat and humidity between the outgoing HVAC air and the incoming HVAC air. So this exchange makes it so the car has to heat the air less, which then requires less energy.
And then for our software component, we have 2 elements, the air quality monitor and the WA monitor. So for the air quality monitor, The primary goal is for it to take real-time measurements of the air quality within the vehicle and on the exterior of the vehicle. So we will have two units, one prior to the cyclonic separator that we discussed earlier, and then one immediately after the Hepa filter. So the benefits of having two are twofold. So first, it will be used to inform the HVAC to selectively intake air. So say there's a lot of pollen or a lot of particulates outside the vehicle, we can use that information and then selectively intake air based on it. And then secondly, we can monitor the filtration process. So having it before and after, we can see the how well the system actually performs, and then determine whether or not the system needs maintenance, if the filter needs to be replaced, and then notify the user if that's the case. And then secondly, we have the WA monitor, which is the name we dubbed. So it's essentially a way to utilize publicly available APIs for accessing local air quality information. So information that's publicly available includes pollen counts, air quality index, as well as the wildfire index. So utilizing that information, we can produce essentially an air quality map of the surrounding environment that the car is driving in. So the idea behind this is that the information that is stored and gathered from within the vehicle using the air quality monitor, as well as the data that we collect from these local air quality indexes, we can produce a map that is shared across vehicles and then is used to inform ride-sharing passengers of the performance of the vehicle, as well as any hazards that are out there based on the risks of the passenger and the vehicle. So utilizing the air quality monitor, the WA monitor, as well as the hardware elements, we can produce a very smart and effective HVAC system for our vehicle. So leveraging these hardware components, we'll be able to selectively intake air based on the air quality outside the vehicle as well as inside. We'll be able to monitor hardware elements based on their performance, and then notify the ride-sharing occupants and drivers based on any risks that are potentially out there based on the outside environment. So the primary goal here is to reduce the user input and improve the user experience. We're developing an autonomous car, so our goal here is really to develop an autonomous HVAC system.
So in conclusion, we solved the problem of allergens in the car, and we did this by using both hardware and software. On the hardware side, we just came up with a better filtering system using the Cyclonic Separator, the Hepa Filter, and the Enthalpy Wheel. And on the software side, we made the HVAC system smart by using an air quality index monitor and the WA monitor. This in turn just reduces user input and makes the whole car just safer for for people with allergies, and also just reduces their stress. For future work, in order to validate the filter design, a proof of concept prototype will be created so that each part of the system can be tested. The prototype will allow for each part of the design to be improved upon separately from the rest of the system. In order to test the design, airborne aerosol particles will be used to visualize the effectiveness of the filter. This test will be similar to the work conducted by Dr. David Rothamer and Dr. Scott Sanders of the University of Wisconsin-Madison on the effectiveness of mask types at using airborne aerosols. Yeah, thank you. We've been Wisconsin Autonomous, and this was our presentation.